Welcome, everyone. Today we are diving into ScyllaDB, the next-generation NoSQL platform. In this session, we will explore how ScyllaDB is specifically designed to maximize performance, efficiency, and scale for modern data-intensive applications. This presentation serves as a comprehensive technical deep dive and implementation guide, providing you with the insights needed to leverage this powerful architecture in your own infrastructure. This executive summary highlights a high-performance, real-time big data database designed for extreme scale. It provides full API compatibility with Apache Cassandra using SQL and DynamoDB via Alternator, ensuring easy adoption for teams already using these popular protocols. There are three primary areas where this database excels. Starting with the architecture, the system is built from the ground up on a shared nothing, shard-per-core model. By using C++ instead of Java, it eliminates JVM overhead and garbage collection pauses, allowing for much more efficient use of modern multi-core processors. Next, in terms of performance, the database is capable of handling millions of operations per second. Most importantly, it delivers this performance with predictable, single-digit millisecond latency, providing the consistency required for mission-critical real-time applications. Finally, efficiency is a core advantage. The platform provides 10 times higher throughput and storage capacity compared to legacy Java-based alternatives. This results in a massive reduction in the required hardware footprint, enabling organizations to achieve more with significantly fewer resources.
Real-time applications, such as mobile chat, face a significant hurdle known as the connection state paradox. When dealing with a massive scale of over 10 million concurrent connections, where only about 500,000 are active at any given time, we encounter critical performance bottlenecks. A major issue is the Java limitation, specifically the stop-the-world garbage collection pauses that disrupt real-time delivery. Additionally, network instability, such as users switching between Wi-Fi and cellular data, demands instantaneous routing decisions. To address these challenges, the system requires high throughput, processing millions of operations per second, while utilizing zero-copy streaming to maintain peak efficiency.
ScyllaDB's performance advantage stems from its fundamental architecture, which utilizes the C* asynchronous C++ framework to address the inherent inefficiencies found in traditional NoSQL databases. On the left, we see the typical thread-per-connection model. In this setup, as the number of concurrent connections grows, the system becomes overwhelmed by lock contention and frequent context switching. This creates a bottleneck where CPU cycles are wasted on administrative overhead and synchronization rather than processing actual data. Conversely, the ScyllaDB architecture on the right employs a shard-per-core design. By pinning a dedicated shard of data and its associated memory directly to each specific CPU core, we achieve a truly shared-nothing, lockless environment. This design allows ScyllaDB to bypass the kernel for user space queue management, ensuring that data flows through the system in parallel without the friction of cross-core communication. This architectural shift from a thread-heavy model to a core-centric one is precisely how ScyllaDB delivers superior throughput and predictable low latency.
This head-to-head comparison between ScyllaDB and Apache Cassandra, based on the 2026 PeerSpot comparison report, provides a clear look at how these two databases stack up across critical metrics. When we examine performance in terms of throughput and latency, ScyllaDB's C++ optimized core allows it to deliver higher throughput and lower latency than the Cassandra standard. User satisfaction remains remarkably consistent across both platforms, with 92% of users recommending Cassandra and 91% recommending ScyllaDB, specifically highlighting ScyllaDB's strength in high-speed data processing. Regarding efficiency and return on investment, while Cassandra offers reliable linear scalability, ScyllaDB achieves a superior total cost of ownership by requiring fewer nodes for comparable workloads. Lastly, ScyllaDB addresses the operational overhead often associated with Cassandra's complex setup by providing built-in auto-tuning capabilities to streamline configuration. ScyllaDB provides exceptional infrastructure and deployment versatility, supporting a variety of operational models. For those seeking a hands-off approach, ScyllaDB Cloud offers a fully managed service on AWS and GCP, eliminating operational overhead. If you prefer orchestration, our Scylla operator for Kubernetes enables high-performance deployments with support for CPU pinning and host networking. For maximum control, ScyllaDB can be deployed anywhere, including on-premises or bare metal, utilizing Docker. Finally, Project Alternator offers a drop-in Amazon DynamoDB-compatible API, which allows you to run DynamoDB workloads seamlessly on any cloud or on-premise environment.
To achieve what we call beast mode performance, your hardware configuration must be meticulously optimized. Starting with the CPU, we require a minimum of 20 cores per node. Scylla is designed to utilize 100% of these resources through a spinning, non-blocking architecture. For storage, the standard is NVMe SSDs in a RAID 0 configuration using the XFS file system for maximum throughput. Regarding memory, you should allocate at least 2 GB of RAM per core and ensure that swap is completely disabled. A critical metric to track is the storage-to-memory ratio, which should not exceed 30:1. For example, 128 GB of RAM is appropriate for managing approximately 3.8 terabytes of data. For those running in the cloud, specific instance types are recommended to meet these high-performance standards. On AWS, look at the i3, i3EN, or EBS-optimized R5B instances. For Azure deployments, the LSV2 series with local NVMe is the top choice. Finally, on GCP, we recommend N2 high-mem instances configured with local SSDs to ensure the system operates at peak efficiency.
Our network architecture and connectivity are optimized for high performance and reliability. Starting with our shard-aware drivers, these native clients for Java, Go, and Python leverage direct shard routing. This allows the driver to communicate directly with a specific core on a node where the data resides, effectively eliminating unnecessary network hops and reducing latency. Moving to the protocol and bandwidth layer, we recommend a minimum network bandwidth of 10 gigabits per second to support high-throughput workloads. To enhance mobile reliability, we have implemented support for HTTP3 and the QUIC protocol. This provides a significant advantage for mobile users by allowing for seamless connection migration between Wi-Fi and cellular networks without the need for TCP renegotiation. Furthermore, it eliminates head-of-line blocking, ensuring that the loss of a single packet does not stall the entire stream of data, resulting in a more responsive and robust user experience.
Achieving maximum performance through data modeling requires a disciplined approach to how we structure and access our data. We should begin by consistently using prepared statements. By parsing a query once and executing it many times, we reduce overhead and secure our application against SQL injection. Additionally, paged queries are necessary to prevent memory bubbles, ensuring that large data transfers do not destabilize the system. At the architectural level, we must prioritize balanced partitioning by selecting keys that distribute the workload evenly across all nodes. Conversely, there are several pitfalls to avoid. Hot partitions must be eliminated, as they create imbalanced loads that bottleneck specific CPU cores. Similarly, we should avoid oversized partitions in rows, which are primary drivers of unpredictable latency spikes. Finally, be mindful of reverse queries. The order by clause in your application must align with the physical data model to ensure queries remain performant and resource efficient. Moving to advanced tuning, we will examine how compaction strategies and workload prioritization impact system performance. When selecting a compaction strategy, your choice should align with your specific workload profile. Size-tiered compaction strategy, or STCS, is the preferred choice for write-heavy environments. In contrast, leveled compaction strategy, or LCS, is optimized for read-heavy workloads by minimizing the number of SS tables queried. Incremental compaction strategy, or ICS, serves as the enterprise default due to its space-efficient design. For time series data, Time Window Compaction Strategy, or TWCS, is ideal as it organizes data into time-based buckets to streamline management and data expiration. Finally, regarding workload prioritization, it is a best practice to isolate latency-sensitive operational (OLTP) workloads from resource-heavy analytical (OLAP) workloads. By effectively managing these distinct traffic types on the same cluster, you ensure that intensive background processing does not compromise the responsiveness of your mission-critical applications. Moving to consistency, availability, and caching, we focus first on replication.
A replication factor of 3 is recommended to achieve the necessary balance between data redundancy and performance. For consistency management, we utilize quorum in single data center environments and local quorum for multi-data center setups. This strategy prioritizes reliability while managing latency effectively across distributed nodes. Our caching strategy involves bypassing the cache for analytical workloads. This prevents full table scans from displacing important operational data, ensuring that frequently accessed hot data remains in memory for optimal performance. As illustrated by the meter at the bottom right, maintaining a replication factor of 3 allows us to operate in a balanced state, providing a robust middle ground between high availability and strong consistency. Observability and the monitoring stack are critical components of our infrastructure. The core of this stack is built on Prometheus and Grafana, providing robust data collection and visualization, with all code rendered in JetBrains Mono for clarity. Our dashboards track essential health metrics, such as P99 latency, throughput in operations per second, and shard-specific performance. To assist in proactive maintenance, the Scylla Advisor offers automated suggestions for system optimization. Additionally, for deep dive troubleshooting, we utilize Wireshark with full CQL dissector support, allowing for granular analysis of database traffic. Scaling mobile chat to over 10 million concurrent connections presents unique challenges, particularly regarding mobile battery constraints and highly asymmetric traffic patterns. The system requires a persistence tier optimized for high-velocity writes to ensure reliable offline message buffering. Our solution utilizes a hybrid architecture, employing real-time server-sent events for foreground communication and push notifications for background updates. By adopting HTTP/3 with Quick, we enable zero RTT resumption, which allows for near-instant connection recovery. As the diagram illustrates, the mobile client connects through a load balancer to ScyllaDB. This high-velocity persistence tier delivers exceptional throughput without the performance penalties of garbage collection pauses. This robust architecture ensures a seamless experience for millions of users across the globe. Now, we will explore the migration paths and ecosystem integrations that support ScyllaDB. Starting with migration, the Spark-based ScyllaDB migrator facilitates large-scale data transitions, while Change Data Capture, or CDC, provides a streamlined approach for real-time streaming updates. Our ecosystem integrations extend to powerful tools like Apache Kafka through its source connector, as well as Janus Graph and KairosDB for specialized graph and time series workloads. To ensure developers can easily connect their applications, we offer native driver support across a variety of popular languages, specifically Java, Go, Python, and Rust. To conclude, let's review the final performance checklist for optimizing your ScyllaDB deployment. Starting with hardware, ensure you are utilizing NVMe SSDs configured in RAID 0 and selecting instances with a high core count, ideally 20 or more. For your client's applications, it is essential to use shard-aware drivers, which allow the application to communicate directly with the specific CPU core owning the data, minimizing internal hops. At the operating system level, we recommend using the XFS file system and running the Scylla.setup script to automate kernel and system tuning. If you are deploying via Docker or Kubernetes, you must pin your CPUs to ensure ScyllaDB has dedicated resources and to avoid the performance penalties of context switching. Finally, observability is critical. Always install the Scylla monitoring stack to maintain full visibility into your cluster's performance. By following these best practices, you can fully achieve the raw performance of C++ while maintaining the familiarity of Cassandra APIs.